So I'm here to talk about IDS rules, which is not my usual thing. Usually I'm up here talking about vulnerability. So first and foremost, I am a vulnerability researcher. I'm not necessarily great at the job, but I do an okay job at it. Lately, though, I would say the last 7 years, I've worked at a defensive company, and I've been writing a lot of IDS signatures, which means that I write a lot of bad IDS signatures. And I've written so many bad IDS signatures. I've written stuff that I know is not going to detect all the possible evasion techniques around the signature itself. I've written stuff that's resulted in false positives, that's given SOC analysts headaches and nightmares. Yeah. I don't want to be like the 5-time divorced person that's trying to offer relationship advice, but I think I've learned a few things about like what makes signatures good and what makes them bad, and I'm hoping that some of that knowledge maybe can be picked up by others. So I have 3 main things that I want to talk about. I really wanted to talk about a 4th, but there's just not enough time. So the 3 main things that I'm going to talk about are using the flow keyword in Suricata and Snort 3, how to deal with request pipelining, and if you don't know what that is, we're going to cover what it is. And then the 3rd thing is going to be talking about insecure by design protocols and what the normal industry approach is for that, and what kind of a cool thing that you can do with one of the IDS engines to like make this a little bit of a better process. You can follow along at home. If you have a laptop with you, you can grab a Git repo that I just made live this morning. It's full of examples that includes PCAPs, rules files, and descriptions of all the stuff I'm going to be talking about in this talk. And if you don't have your laptop with you, you can always grab these later. So the first thing I want to talk about is the flow keyword. It's really a weird thing that results in false positives a lot. People leave this off of their rules. So there's this flow keyword that's supported by both Snort 3 and Suricata that lets you define what direction you should expect to see a network packet go in. And so you say like either this is going to the server or from the client. They both mean the same thing. That means that it's a request generally for an ICS server like a PLC. Or you can say the flow is going from the server or to the client. They both mean the same thing. You can word it either way in the IDS engines. That just means that it's typically a response message from an ICS device. So here's an example of a bad rule, right? This is this rule here that says bad rule. This is an Ethernet IP list identity request. And this would be a bad rule because we don't have a flow keyword. What this is saying is, if you see this TCP packet from any host, any port, to any host port 44818, and it contains these 2 bytes at the beginning, 6300, you want to make an alert, basically saying, hey, somebody's doing a list identity scan. Maybe they're like scanning your network, looking for what's available. And the reason that that's a bad rule, I'll go into in just a second. But the better rule is to add this flow direction. You want to say that this is a packet that's a request packet, so it's going to a server. The reason that this is a bad, or the original rule was a bad rule, is because Ethernet IP uses TCP port 44818. Operating systems have, or TCP has a source port and a destination port. Operating systems typically give source ports greater than 1024 to any network client. So if you have a web browser, for example, and you open up a connection to Gmail, your web browser may be assigned to the source port 44818. This means that if you make a request to the server and then the server sends you a response, if that server response happens to start with the bytes 6300, the rule, the bad rule above, will alert and trigger, and you'll get a false positive. That's a bad thing. So I wrote a little script. It's in the GitHub repo where you can actually scan your rules file and look to see. Basically, it uses a rule parsing library to look through all the rules in your rules file and will analyze all the rules and say, hey, do any of these define ports that are greater than 1024? And if so, are those rules, are they missing a flow keyword? Anything that's missing a flow keyword, it will put a little warning at the end of the script, and it will also return 1 if there were any results found, and it will return 0 if your rules file is clean. So that's cool. Downsides to this. Everything has a downside, so when you enable weird features in rules or you do weird stuff with IDSs, there's always a downside. Anybody that doesn't tell you about the downsides is trying to sell something. But in this case, the flow keyword will fail if you miss the initial TCP handshake. And so why might that happen? Well, if you have a plant, maybe your HMI has been talking to your PLC for 4 years and the TCP connection has never shut off and restarted. Hey, I've seen it happen. And then you decided to plug an IDS engine into the network, and you did so in a way that didn't require creating a new TCP connection, well, your IDS will no longer be able to like tell which direction is the server and which is the client, so the rules will never match. If you have like some weird distributed processing system where you have like, I have no idea how this really works in the real world, but if you have IDS sensors that do like load balancing between different processes, this might also fail. Still, I think it's a trade-off that's worth it just because the false positives get kind of funny. Like we get telemetry back and we have seen like hundreds of thousands of false positives, and guess what? The other side of the connection is TCP port 443, and the, one side is some ICS protocol. All right, so that was the number one. We're on to number two. Number one was easy, I think. Number two is one of my personal favorites, though, because this goes back to the S419 CTF. I used to be one of the people that ran the CTF here, and I made this fun challenge back in 2019 that I guess broke everybody's brains because nobody solved it how I intended it to be solved. It is a challenge that required you to use request pipelining to evade a firewall. And this actually has a lot applications for IDS too, and I actually made the challenge source code for this available on that GitHub repo. You can, again, go clone it. But what is request pipelining? So in the industrial space, actually in almost any network protocol that uses TCP as a transport, you can load multiple requests into one TCP packet. In this case, I have a single TCP packet with two Modbus TCP requests in it. So for example, one of these Modbus TCP requests might be a read register command, and then the second command might be a write register command. And this would be a great way to evade bad IDS rules, because bad IDS rules will look to fixed offsets in the packet and say, hey, is byte 5, which is the function code or what have you, is it a read or is it a write? It's a read. Oh, well then I'm just going to ignore the rest of the packet because I don't care. And that's how you use this kind of technique for evading those bad IDS rules. So most TCP protocols support request pipelining. Like every single device I've seen that implements Modbus TCP supports it. Like every device I've seen that implements Ethernet IP SIP supports it. Proprietary protocols also generally support it, and it's just kind of a legacy problem that comes from the way vendors packetize requests internally. So you can use this to evade bad IDS signatures, also application layer firewalls. I won't name names, but there are some out there where you can use this. And this actually can result in false positives too, because if you have a bad rule that simply looks to the first byte and says, okay, that matches, and then runs something like a regular expression on the entirety of the rest of the packet, well, a pipeline request might trigger that regular expression on occasion. And if your IDS sensor doesn't record PCAPs, like if you just get the alerts, you're going to be in for a bad time because you're going to see this alert flag, and then you're going to be like, wow, well, I wonder why it happened. Maybe it was a real attack. I need to go investigate. I need to go do a forensic analysis of this HMI system and see what's going on. And that can be just a nightmare. So the basis of the S419 CTF challenge, it was a Cisco Talos finding back in 2017. They had this awesome vulnerability. It was a crash bug where you send an Ethernet IP request to a certain PLC. The PLC crashes when it processes its request. The thing that really jumped out to me in this was this quote where they said, additionally, the crash can be triggered by prepending any number of 24-byte blocks of null characters. So the explanation to me, I don't know. I see Joe in the audience. I don't know if Jared is here, but Jared maybe can answer this question. Maybe Joe can too. But I sort of got the suggestion, at least from the write-up, that it was found via fuzzing, this whole 24 null byte sequence. But what this really is request pipelining. So what's going on here? The Ethernet IP protocol, this is what the Ethernet IP header looks like. It is 24 bytes long, and then if you have a SIP request embedded inside of this, it would come after the Ethernet IP header. So 24 null bytes would be command 0, which is a no-op command. And then the length field would also be 0, meaning that there's no payload. So that means the packet is only 24 bytes long. Everything else is set to 0, so you have a null session handle, no status bits set, no sender context, no options. But basically a no-op is, it just tells the remote device, hey, take this request and throw it away. Like, we don't care about it, and then continue processing whatever other requests you have. So this was the malicious packet from that advisory. This malicious packet is actually also a no-op request, except it has a really big length field. The length is stored little endian, so the length is FFE8. Probably what goes on internally in the PLC, you add 24 to the length. And if you add 24 to this, you get 0 as a 16-bit integer, so it's probably an integer overflow, which resulted in some memory corruption. But this is really just a no-op request. Probably it just was a memory corruption bug that crashed the PLC. But when we prepend that 24 null bytes, or any multiple of 24 null bytes to the beginning of that request, we have a no-op, right? So we have a 24-byte no-op, and then the PLC processes the rest of the request, and then the PLC crashes. So the question becomes, well, what happens if we send a slightly different packet? We send a no-op command with a 1 in the length field, and then because there's a 1 in the length field, we now need to have an extra byte at the end of this packet, so we need it to be 25 bytes long, not 24. Well, guess what? The PLC still crashes. Okay. This is what that request would look like. So we would have pretty much the same thing, except now instead of 24 zeros, we have 25 bytes with a 1 in the length field, and then we can put any character we want in those kind of remainder bytes. Because the PLC, again, is just going to look at this, say, okay, there's a NOP, it's 25 bytes long, take those 25 bytes, throw them away, what's the next request? Okay, I need to allocate this FFE8 plus 24 bytes. I allocate 0 bytes of memory, I try to copy a big thing into that 0 bytes of memory, and I crash. What happens if we put 2 in the length field? You can kind of see where this is going, right? We can actually make no-op requests of any length up to that thing that actually ends up crashing the PLC, and we can put whatever data we want actually in a lot of those fields. I think even the session ID field could be random data. You could probably mess with the options fields too, but you can have a lot of potential prepend strings to this. So this makes it really difficult to detect with kind of classical IDS systems. Because the classic IDS just does matching of bits and bytes in a packet stream. And this you really need to have a whole bunch of logic, because there could be 1 no-op request before the crash, there could be 2 no-op requests before the crash, there could be 3. They all could have their own length field, and you can't write like a loop inside of an IDS signature. That's not the way IDS signatures work. So you need a better way to deal with this. And by the way, if you want to play with this at home, there's this enip info script that you can run. Probably a lot of people are familiar with it, where you can like scan a PLC and it will give you the vendor name and all that stuff. If you take that nmaps enip info script and you change the enip query to add 24 null bytes to the beginning of the list identity command, it will still work perfectly, because the PLC will just take the no-op, throw it away, respond to the list identity command, and the nmap script will work otherwise unmodified. Kind of fun. So, and that will actually probably evade some detections, at least in the IDS space, just because rules are written badly, unfortunately. So how do we detect it? Well, really there's 2 ways to detect pipeline requests right now. One is to use a protocol preprocessor, and I'll talk about that. I think Snort 3 has a different name for them. I guess they're called inspectors or something. I've always called them preprocessors, but we'll talk about what they are, how they work, and what their flaws are. The other way is to just write rules to detect pipelining, which I actually recommend you do anyway. And I'm really like struggling, but I'm hoping that I'm going to have this third way done for the Suricata IDS, which is to have universal pipeline handling. And there's infinite many bad ways to try to do this. I've like run through the thought exercise. I'm like, well, you could write a script to generate rules based on a rule to look for pipelining using like some byte extraction techniques, but then you end up having like an explosion. You basically, if you have 1 rule, you need to have 15,000 accompanying rules to look for all the possible pipeline methods of that rule. So how do you use the preprocessors? Well, first of all, you have to take your IDS configuration and enable those processors. So in Suricata, there's like the Suricata YAML file. In Snort 3, I think it's like a Lewis script you have to edit to modify the configuration, make sure the preprocessors are enabled. In this case, let's talk about Modbus a little bit. Everybody loves Modbus, right? Citation needed, maybe? I don't know. So in this case, we would look for a Modbus request where we try to write to register 40,000, right? And Modbus has the same problem where I could have infinite number of read requests before a write request, but the preprocessor actually handles that for us. If we put the TCP alert, or not TCP, but we would actually say alert Modbus any, that will tell the rule that it should only fire for packets that have been pre-processed by the Modbus preprocessor. But then we can add this directive, and we can say in Suricata, we can say tell me if somebody's trying to write to register 40,000. Snort 3 is not quite as good. Sorry to pick on Snort, but this one is actually not quite as good as Suricata. I should say Snort 3's Ethernet IP preprocessor is like 1,000,000 times better than Suricata's publicly available Ethernet IP preprocessor, so I don't want to play favorites. But in the case of Snort 3, you can just say, here's the function code, and then you can only do content checks on the actual request data. You don't get this sort of like meta thing where I can say, is it address 40,000? And that Suricata's way of doing it I really love, because there's like an evasion inside of an evasion that you can do, where you can say like, hey, if the request was made to write to register 39996 for four registers total, the Suricata rule will pick that up, and it will be like, yeah, that's an attempt to write to register 40,000. In Snort, I actually don't know how to do it to detect that double evasion, and hopefully I can think of a way, but hopefully some Snort 3 wizards can tell me. But there's examples of this in that GitHub repo as well. So the preprocessor trade-offs, right? One, preprocessors do require CPU time, right? The preprocessor is a chunk of code. In Suricata, a lot of them now are written in Rust. Some of them are still written probably in C or C++. Hopefully they update those. But the real thing is, if the packet is formed, the preprocessor is probably going to say, hey, this is not a properly formed packet. I'm not going to populate any of the fields. That happens a lot. And that's usually the kind of thing that you want to detect, right? Which is, if I have a pipeline request where maybe the third request in the pipeline is a malformed request, that could be some kind of buffer overflow trick or something like that, and an evasion on top of it. So maybe it's like really important. So that's the thing that I don't like so much about the use of preprocessors, is just that like those sanity checks can kind of get in your way. There's some other trade-offs too, like the Snort 3, like their Modbus preprocessor, I don't like it as much just because it doesn't have a lot of like useful data, like generic function codes, like just tell me if it's a write, tell me if the register that they're trying to write to is this. But that Modbus data field that Snort 3 has is amazing, and I love it, and I wish every single preprocessor had something like it, because sometimes what you want to do is you want to say, hey, tell me about a certain ICS protocol function code, and then inside of the kind of rule that triggers, that starts to trigger at least on that function code, you want to get at the complete request data and then just do your own content checking within that request. You can do that with the Snort 3 Modbus preprocessor, and you can't really do it inside of the Suricata preprocessor. So yeah, makes me a little bit sad. Anyway, so let's talk about the way number 2. So using preprocessors is the one thing I wish more people would do. But method number 2 is that you can detect pipelining itself. So what you can do usually with protocols is they'll have a fixed length, or they'll have some kind of length field in them. And you can extract the bytes out of the packet, and usually you have to do something like this byte math statement, where you basically say, hey, this protocol, it says that the protocol identifier, that's the bytes 00, they're always 00 at offset 2, so that's kind of like a sanity check, make sure this is actually Modbus. Then I'm going to extract the length field using this byte math statement, and then I'm going to add 6 to the length field, because the length field doesn't count the header bytes, which there are 6, so there's this 2-byte transaction identifier, 2-byte protocol identifier, and 2-byte length. That's not counted in the length. But then I'm going to see if there is data in this packet at that offset. That's what that is data at statement means. And I wish that you could use, there's another verb in both Suricata and Snort 3 called delength, but you can't compare delength to variables. So basically what you're doing here, though, is you're extracting this length, you're storing it in this variable MB length, and then you're saying, is there data at that offset, MB length? And if there is, this is probably some kind of pipelined request or buffer overflow or something weird. Somebody is just doing something weird. So again, I have examples of this in that GitHub repo. You can take a look. There's a like lesson 2, I think, directory in there. Way number 3, this is in development. This is like my dream that I wish I knew how to implement right now, but like I said, I'm doing this in Suricata, and Suricata is written, a lot of the stuff now is being written in Rust, and I suck at Rust programming because I'm old, and I grew up programming in C. But I want to do something like this pass bytes verb. So it would be very similar to the last rule, where we extract out the length field from the packet, and then we would basically say, pass the bytes the remaining bytes in this packet back to Suricata's input. Like, use all the header fields that were already there as part of the packet, just set a new payload for the packet to be located at the offset, and then rerun all the existing Suricata rules in the rule set against that packet as though that was a brand new packet. And the thing that I liked about this technique is that it gives you kind of, it's basically like recursion. You know, if we notice a pipeline request, we'll move the pointer to where the next request starts. We'll pass that back as a new packet. And hey, if that new packet has pipeline requests of its own, they will also be handled. And then I thought, well, I probably need something like a maximum depth just to avoid like addition mistakes or integer overflows or other bugs that could result in an infinite loop, because, you know, if you're trying to like pass a mangled packet, what if the offset, or what if the length is 0? That would be really bad, because then you would be stuck running this rule over and over and over again, and the IDS engine would be pegged at 100% CPU time. So that's kind of how I hope it will work, and I hope if I actually get it working, you know, I'll be, I don't know, a Suricata wizard at that point. So I mentioned 3 things. So this is the 3rd thing, insecure by design protocols. So this is where I'm going to pick on Dale and actually us a little bit too. There was this piece of malware called Frosty Goop, and it is a Modbus piece of malware that goes after a very specific type of PLC, I guess I'll call it. It's a specialty purpose PLC, though, that's really meant for running HVAC controls. And the malware, you know, writes to a very specific register to turn heat off, right? This is a thing that impacted some buildings in Ukraine. You know, we wrote some rules to look to see if somebody's trying to write to this particular register, you know, with this particular unit identifier, and that's fine, but it also really sucks. And then years ago, Digital Bond wrote a whole suite of protocol IDS signatures, part of what they call the Quick Draw project. And I love the Quick Draw project, don't get me wrong. But those quick draw signatures, pretty much they only detect bad stuff if it's coming from not an engineering workstation or not an HMI, is how the rules are like set up initially. And they're basically either, well, the Frosty Goop malware, at least allegedly, went through an engineering workstation. So the alert, you know, the quick draw signature wouldn't actually fire in that case, because it's, you know, the EWS is basically compromised and it's sending the malicious commands. But yeah, so beyond that, you either have, you miss the attack, or you set the alert for everything on your network as the source, and then you probably spot the attack, but you might get a whole bunch of noise. And the reason that you get a whole bunch of noise is that you're writing a signature that basically says, hey, somebody's using this protocol to write to this register. Let's pretend again that it's register 40,000. That's not the actual register, I don't think, that was in use, but let's pretend for the sake of argument that it is. So we want a rule like this that basically says, hey, if somebody is using the Modbus protocol and they try to do a write to this register, it means that they're trying to shut off the heat. Well, what sucks about this rule? This rule sucks because it's going to detect everybody trying to write to register 40,000 for all of the devices on your network. And maybe some of those devices on your network are things where writing to register 40,000 is normal and isn't going to cause the heat to turn off. You know, maybe you have a lot of different types of PLC on your network. So what you want to do is kind of differentiate the benign, so the writing to register 40,000 for hosts that we don't really care about, from the actual special purpose device where writing register 40,000 shuts off a bunch of people's heat. And so normally the way we do this in, you know, detections land is that we have the rule that fires for everything, and then we have some kind of mop-up where we have an outside engine that takes a look to see, all right, are there alerts that match that rule? Were any of those alerts against an asset that I know is actually vulnerable to this issue? And then I'm going to basically bubble those up to a SOC analyst to look into. And the problem with that approach, at least in my view, is that you might have errors in labeling your assets. You might have, you know, a new SOC analyst that sees like a severity 0 alert in the, you know, alert log and gets freaked out about it. There's coding mistakes. There's all kinds of problems. So there's got to be a better way, right? This is a way to do it with Suricata. Maybe you can do this with Snort 3. So far as I know, Snort 3 doesn't have this kind of capability, but they have this thing called data sets. So basically, you can have a rule that assigns a host to a data set, and then you can have another rule that checks not only for the, you know, contents of the packet being an attack packet, but you can also say, is the target of this a member of a data set? And the reason this is cool is because you can modify these data sets on the fly while the IDS is running. You don't have to go in and edit a config file and then restart the IDS the way you do with like those variable names in the rule, where you would say like, TCP alert from known bad hosts or unknown hosts or whatever. So the way that this looks is that you write a rule like this first rule that basically has a signature that will analyze and it will fire when the asset is a known vulnerable asset. And this rule is basically, what it's doing is it's saying this IP.source, and it's saying, set that as my sticky buffer, and then add that IP source address to this data set called vulnerable widgets using this dataset set command. And then we have a second rule that's an alert rule, which says if there's an attack packet, first, I see that it's an attack packet and I'm maybe going to trigger an alert, but first I look up and see if this actually should say the IP.dest, good catch, the IP.dest of this packet is in the vulnerable datasets widget by looking to see if it's in dataset:isset. And I have a kind of contrived example of this, not using Modbus, but with an invented protocol. I have a server simulator. The client, you could just use Telnet or Netcat, but 2 server simulators, one for a vulnerable device, one for an immune device, and an alert rule that only flags on the actually vulnerable device when you run the evil command against that device. So I'm going to skip over this because I'm running out of time, but I'll have Tony Robson is an amazing guy. He has a book on writing Suricata rules, and I'll have a link to that in the end. But this is just kind of one more thing to watch out for. So one last thing about data sets is I was doing this with a rule to add the device to the data set. You can't do that. Like if you can't actively scan your network to get that first rule to fire, you can do outside dataset access using a Unix socket with Suricata, which means that you can basically like connect to your Suricata engine while it's running and tell it, hey, this device belongs to this dataset, and make your alerts actually alert when you want to. So in summary, there were 3 main things. There's setting that flow direction to client or to server. Make sure you do that for any rules that have TCP ports defined above 1024. Use those preprocessors if they're available for your protocol. And if they're not available for your protocol, think about implementing them, although I think they kind of stink to implement still. So if it's like a proprietary protocol, maybe you're not going to do that. 3, write generic IDS pipeline detections or protocol pipeline detections. You can do that pretty easily by extracting the length fields and then seeing if there's data later in the packet past what the length should be. And finally, use those data sets to kind of prevent the over-application of your rules and reliance on external tools. There's some further reading if anybody wants. I definitely recommend the OISF Discord server if you're a Suricata user. They're amazingly helpful. I go in there and ask really stupid questions all the time, and they don't make me feel like that much of an idiot. So yeah, do that. Donate to OISF if you use Suricata for sure. Tony Robson has a book called the Suricata Operator's Handbook that's really worthwhile reading. I learned new things from it, and it's like 10% done. So it's a pretty good read. And finally, that GitHub thing again is there. Oh, and if you use Suricata, read the Snort 3 documentation too, because there's a lot of stuff that's not documented in the Suricata documentation that works, that kind of carried over from Snort that you can use. So open up for questions. Please walk up to the microphones if you have questions, and if there aren't any, I'll be around. So. Okay, no questions. So all right, thanks.